All right, everyone. Thank you so much for joining us today for our research seminar. My name is Cinnamon Moffett, and I'm the research program manager here at Oregon State University's Hatfield Marine Science Center, located in Newport, Oregon, and I will be your host. This is a hybrid event, so welcome to everybody that's online as well. For folks that are in the room, looks like most of you have been here with me before, but remember, if you have a question for our speaker today, please raise your hand and I will bring you a mic. That way the folks online can hear your questions as well. For folks that are online, if you have a question, Roseanne is in the room. She's our volunteer for today. If you put any questions into the chat box, she will read them out to our presenter, and that way we can get all your questions answered. I wanted to just do a little bit of a couple of quick announcements about events that are coming up. So just wanted to let you all know that next week's seminar on June 15th, Emily Edem is going to be here from the Coastal Sediment Dynamics Lab at Oregon State University, talking about the rapidly changing sediment dynamics in the Arctic coast. So come join us for that. I also just wanted to remind everybody about our next Science on Tap, which is June 20th, where we have staff from DLCD coming to talk about planning goal 18 and the changing Oregon beaches and dunes. And also wanted to let folks know or remind you of our Markham Symposium on June 22nd from 2 to 5 in this room. The Markham Symposium is where we have all of our student researchers who have received awards present their work. And that is open to the public, and everyone's welcome to join us at that event. And if you are interested in any of those events or you're curious about other things happening at Hatfield, you can go to our events page on HMSC and check out all the details there. But for today, I want to just do a quick introduction of our speaker. Will Fairchild got his undergraduate in oceanography and applied mathematics from Humboldt State in 2015, and his master's in oceanography right here from Oregon State University under the mentorship of Burke Hales. He's been an ORISE researcher with EPA since 2021, and he told me he was all excited because he was taking a full-time position with EPA, and I was so excited he was going to be here with us. And then he burst my bubble and said the job is actually in Washington, D.C. But we're very proud of him for getting a full-time position with EPA. It's just going to be in Washington, D.C., and we'll keep him on our list to get information from. So I am very thrilled that Will is going to be presenting today. Will is a partner of mine and Hatfield's in our climate monitoring station effort that we are getting off the ground. And so I'm just excited to learn a little bit more about his background and some of the things that he's been working on. So I'm going to hand this off to Will. Turn your mic on.
Hi, thank you for coming. Again, my name is Will Fairchild. I'm an ORISE researcher with the EPA, and today I'll be discussing some of the work that I've been a part of for the last 2 years with the EPA and talking about evaluating common sensors for ocean acidification research in Tillamook Bay, Oregon. So just a quick overview of what I'll be talking about. I'll be discussing what is ocean acidification for those of you who might have a rusty background in your chemical oceanography, but I'll make it quick and easy. How do we measure acidification? What does monitoring look like in Tillamook Bay, Oregon? Some results from the last 5 years of continuous observations, and then lessons learned and some recommendations that we think are important for the community. So a main question, if I could sort of synthesize what our research has been about, is how do we evaluate the performance of sensors for ocean acidification detection? So a brief primer on ocean acidification. I think without talking about atmospheric CO2, we can't fully understand the dynamics of ocean acidification. So this is a graph of the last 800,000 years approximately of atmospheric CO2. This is taken from a couple Antarctic ice cores. And what we see are these sort of sawtooth patterns in the ice core record here. And these indicate sort of interglacial and glacial periods. But we see sort of towards the end of the graph, when we reach sort of the modern day, there's a giant spike in the graph. And in fact, these values almost look like they're about to jump off the graph. And that's because during the Industrial Revolution, we started burning fossil fuels. and these fossil fuels contributed to increased atmospheric CO2. So this is that figure sort of blown up, or that little bubble that I had circled blown up. Should be a familiar curve. This is the Keeling curve made by Charles Keeling starting in 1958. And what we see is we have a steady increase in CO2. There is a seasonal pattern, and that pattern is largely due to sort of like the decaying and growing boreal forests in the Northern Hemisphere. But we see an increase and a rapid acceleration in CO2 in our atmospheres. There's a Twitter handle called CO2 Earth. And if you go to it, they update the Mauna Loa station CO2 information. And as of yesterday, or sorry, 2 days ago, the atmospheric CO2 concentration was 424.72. And that was up from 3.5 from just a year ago. And when I finished college, we had just passed 400 parts per million. So we are rapidly increasing the amount of carbon in our atmosphere. So this is that same graph, but now I've depicted Station Aloha, which began recording pH, surface ocean pH, and surface ocean PCO2 beginning in the late 80s. And what we see is as we have a concurrent rise in ocean CO2, we have a concurrent rise in surface ocean PCO2, or the partial pressure of carbon dioxide. And we also have a gradual declining of ocean pH. Since the Industrial Revolution, we have declined ocean pH about 0.11 units or so. And that corresponds to an uptake of approximately 30% of all carbon that's been burned since the Industrial Revolution. So ocean acidification is sort of that effect of declining ocean pH as a result of burning fossil fuel combustion. This is a sort of breakdown. It's a very simple breakdown of what happens when CO2 enters the water. So when CO2 is equilibrating with ocean surface waters, it contacts H2O and it forms carbonic acid, which quickly dissociates into bicarbonate and then carbonate. It also releases a proton during this process. And if we sort of simplify this methodology, or this breakdown and speciation of the carbonate system, what we get as a net result of carbon entering the oceans is an increase in bicarbonate, obviously an increase in CO2. We have an increase in the hydrogen ion proton concentration, which results in a decrease in pH. Now, we also have a decrease in the availability of the carbonate ion. And the carbonate ion is an important sort of part of the story of ocean acidification, mainly because marine calcifiers rely on carbonates, calcium carbonate, to form their shells in situ. Now, this is some work that was done, I believe, here at Hatfield a couple years ago. And what it shows is the Pacific oyster larvae raised under more favorable conditions in this upper, sorry, I think the cursor has been over here. It shows oyster larvae raised under favorable conditions under 4 days, and then under unfavorable conditions. So they manipulated the water so that the carbonate ion concentration was less in these bottom panels. And as a result, the shell formation was hindered and the stability of the actual organism was compromised. Now, we use a phrase, or not a phrase, but a term called aragonite saturation state. And that's defined loosely as the calcium carbonate concentration and the calcium concentration and the carbonate concentration. And when the aragonite saturation state is below 1, it favors shell dissolution in situ. So in the water itself, the shells will start to begin to dissolve when aragonite saturation falls below 1. So aragonite saturation less than 1 indicates that the water is corrosive to calcifying organisms. So this is a model of what the surface ocean will look like at the end of century. This is aragonite saturation state, and red indicates very low to undersaturated conditions, so bad for organisms that want to calcify. And these lighter colors to blue represent really good, healthy conditions where the water is actually supersaturated with respect to calcium carbonate. And what we see is that as we increase throughout the century, the high latitude regions become more corrosive with respect to calcium carbonate. And that's largely due to the fact that the higher latitude regions are colder. And as we increase CO2 in the atmospheres, the solubility of these higher latitude regions will increase their CO2 concentration. And as a result, the calcium carbonate or aragonite saturation state will fall. So why do we focus so much on saturation state when there are other things to worry about, like simply just pH falling? Well, the shellfish industry represents a multi-billion-dollar industry, and it's a vital food source for millions of people around the world. Now, we cannot directly measure calcium carbonate, or we cannot directly measure saturation state. So what we need to do is create a sort of robust OA monitoring network and sensors to use as a sort of proxy to calculate saturation state. So again, our main question is, how do we evaluate the performance of sensors for ocean acidification detection? And in this case, we're going to focus primarily on the detection of saturation state. So how do we measure OA in the field? And again, OA stands for ocean acidification, if I didn't already say that. Now, in general, for the carbonate system, we have to measure 2 of 4 parameters. So pH, or the ion proton concentration, the hydrogen ion proton concentration, DIC, which is a combination of carbonates, the carbonate, bicarbonate, and carbonic acid. We can measure alkalinity, or we can measure PCO2, which is the partial pressure of CO2. In general, though, commercially available sort of autonomous systems to measure alkalinity or DIC are not readily available, although there are some experimental designs to have in situ autonomous alkalinity measurements. They are expensive and they require a lot of reagents and upkeep to do. So instead, the technology for pH and PCO2 is a little more relatively advanced, and we rely on sensors for pH and PCO2 to calculate out the full carbonate system. So one of these instruments is called the YSI sonde. It's a glass electrode pH. It has a manufacturer uncertainty of about 0.2 pH units. And the uncertainty is important because if you go out to measure, for example, the bay here, the pH might be 8 or so, but with the YSI, you have an uncertainty of 0.2 units. So it could be 8.2, could be 7.8. The YSI sonde is user-friendly. It's widely available. It has a nice little handheld device that you can take with you out to the field and deploy sensors very easily. But there are some issues with drift and calibration. So we actually used the YSI sonde, and we switched over to the EXO sonde in about 2019, and it's been fairly useful for us. The other instrument to measure pH is the SeaFET, and that's modeled here on the right-hand side of this cage. It measures pH. It's an ion-sensitive field effect transistor. The manufacturer uncertainty is 0.05 units, so it's much better than the YSI, but it's still considerably larger than a lot of ocean acidification metrics would like it to be. It has stable readings in the long term, so it's good for long-term deployment, and there's no reagent, so you don't have to worry about reagents. And it's becoming widely adopted in ocean acidification circles. Now for PCO2, we have commonly used the Sunburst sensor SAMI-CO2, and it determines PCO2 through a colorimetric method with a pH-sensitive dye. And the manufacturer uncertainty is approximately 2 microatmospheres, although we believe that the SAMI-CO2 has probably a much larger uncertainty than that. However, we were not able to test that in our studies. The water is equilibrated across a CO2 permeable membrane. And the SAMI is challenged by biofouling because within this cage here is where the equilibration occurs. And during the summer months, this can get pretty gross and difficult to adjust for, sort of like drift corrections and doing biofouling corrections. And again, this list is not exhaustive, but it does represent some of the commonly used instruments that we deploy in the field. So how do we measure ocean acidification in Tillamook itself? Tillamook Bay is 2 hours north of Newport. If you haven't been there, it's a really beautiful place. We have a station underneath the Garibaldi dock that we have been operating for approximately 5 years continuously. And that is represented by this cage here, which can house the SAMI-CO2, the YSI, and the SeaFET pH, which I had just talked about. And it sits approximately 1.5 meters off the bottom of the water at all times, even during like high and low tides. And again, it's been in continuous operation for 5 years. So we have a pretty novel and robust data set to look through. Part of the data collection involves cleaning the sensors frequently. So we go out about once a month in the wintertime and about twice a month in the summertime when biofouling is much higher. We conditioned the SeaFET, which is located here. This is actually a SeapHOx. The SeapHOx is a combination of a CTD sensor, which is a conductivity temperature depth sensor, an oxygen sensor, and the SeaFET pH probe. We conditioned this in a seawater tank according to sort of accepted standards in the community because of issues with sort of like the ionic strength of seawater and the way that the sensors respond to it once we deploy them in seawater. Down here is a proprietary instrument that we use because we take check samples when we go out to the field. We sort of take triplicate check samples with a Niskin bottle. We deploy it close to the sensor package at the base of the water column. And then we deploy the Niskin bottle, we release the Niskin, and then we capture the water in sort of glass amber bottles, and we poison them with mercuric chloride. And this is a sort of standard procedure for capturing discrete water samples for carbonates. This system itself is really cool. It's built by my old graduate advisor, Dr. Burke Hales. It's called the Burkulator, and it's capable of measuring PCO2 and DIC directly out of the bottle samples. And so from that, we're able to calculate through the carbonate system, pH and aragonite saturation state and alkalinity. So it's a very useful tool that we have in our back pocket to sort of ground truth the instruments and create a set of like calibration standards for our instruments in theory. So why do we use Tillamook as a place where we have decided to set up our operations? Well, there's extreme sort of biogeochemical variability in Tillamook Bay, and it can represent the future ocean acidification scenarios for other estuaries and wetlands in the Pacific Northwest and elsewhere. It's also the site of historic water quality studies conducted by the Tillamook Estuaries Partnership and the Department of Environmental Quality. It's strongly influenced by eutrophication and anthropogenic forcings. And the time series that has been built over the last 5 years, thanks to a lot of the folk at the EPA, make it so it's not very comparable with many estuarine ocean acidification research studies. So what we learn from this research can be novel and useful for future ocean acidification work. So just some results, some initial observations from our work in Tillamook Bay. What we have up here is a time series from 2017 through 2022. In green is salinity, in red is temperature, purple is pH, and then PCO2 is in this cyan color. And it's important to note that these are direct observations of all parameters. And what you can see is that there are cyclical cycles. There are cycles in temperature, salinity, PCO2, and even pH. So Tillamook Bay is a highly dynamic biogeochemical and hydrological environment. In fact, we see salinity swings from 0 all the way up to 33 at times. Temperature can range from 4 when it's very cold and snowy to 20. pH can range from about 6.8 to 6.9 during really intense sort of flooding events that are sometimes associated with atmospheric rivers. So it can range from about 6.8 up to 8.5 or so. And then PCO2 has been recorded as low as 100 microatmospheres, which is fairly low and undersaturated with respect to the atmosphere, to well over 2,000 during times of really intense sort of productivity in the bay. It might be difficult to see, but there are little dots along here scattered around. Those represent all of the check samples that we've taken. And this shaded area is sort of blown up here. And what I wanted to highlight was the fact that we have a lot of diurnal and diel variability in the carbonate system and in the hydrological system. We even have event scale sort of dynamics here. We have an elevated PCO2 over the course of several days. And that was in tandem with a drop in pH. And if I were to sort of overlay the upwelling index for this time period, we would see that this was directly related to upwelling off the coast. So upwelled water contains very low pH, very high PCO2, and low saturation state. And so it was upwelled to the coast and then sort of like tidally infected into the bay. So the summertime is largely influenced, the in-bay processes are largely influenced by upwelling during the summertime. And during wintertime, we see downwelling as the dominant presence in the bay, which delivers pretty low salinity to the bay itself. So I talked about our check samples and the utility of taking check samples. And ideally, check samples are used to sort of ground truth instrumentation itself. And they're used to calibrate instruments and also sort of design a way to understand how uncertain your measurement is. So if you go out to the field and you have a sensor and you take a check sample next to your sensor, ideally you can create a sort of regression over time of your check samples versus your sensor. And that can tell you, if you calculate the RMSE or the uncertainty of your curve, that can tell you how uncertain your measurement is. It can give you a sense of accuracy of your sensor. What we found is that when we looked at the check sample data versus the sensors, so here we have the SAMI-CO2, this is the YSI in the middle, and we have the SeaFET pH on the right. What we find is, compared to the literature that's been published for these sensors, our data doesn't look exactly like the published data. In fact, we seem to have R-squareds or regression coefficients that aren't as robust as some of the published literature. And there's a couple reasons we think that's happening. When we deploy the Niskin next to the sensor, we think there is some heterogeneity in the water column. So there could be a mismatch between temperature and salinity, or PCO2 and pH between the sensors and the discrete samples that we're taking. And the reason I'm focused on this for a minute is because we wanted to use the sort of RMSE here as a way to understand how well we're measuring these ocean acidification metrics in Tillamook Bay. And we were unable to come up with a better method than to rely on the manufacturer-based recommendations for uncertainty for the SAMI. We were also unable to do that for the YSI, but for the SeapHOx, we came up with what we believe is a novel way to sort of address measurement uncertainty with the SeaFET pH. So what that looks like is this. So we used certified reference material. And if you're not familiar with those are very commonly used sort of oceanographic reference materials. They contain a very high accuracy and precision of alkalinity in DIC, or dissolved inorganic carbon. And from that, we can calculate pH very accurately. So what we do with the SeaFET is it has a little cap on the top of it, and you can take the cap off and sort of insert water and do a discrete sample if you wish, or you can take off the cap and insert the CRM. So what we do is we take the reference material, we put it in the SeaFET, and then we leave it in the tank overnight so the temperature of the water can sort of equilibrate with the temperature of the reference material. And in the morning, we take a sample. And we were able to create this sort of regression curve over the course of about 18 months or so, because we only do this about once a month when we go out to the field. And we got an RMSE of about 0.036. And I'm going to focus sort of on this number for a few slides because it's useful in sort of how we are assessing sensor performance. And again, that goes back to the main question of how do we evaluate the performance of sensors for ocean acidification detection? Because we want to hone in on the uncertainty and make the uncertainties as small as possible for our measurements. So I want to take a quick second to talk about alkalinity, which may not be everybody's favorite subject, but alkalinity for large swaths of the ocean is largely conservative with respect to salinity. So step changes in alkalinity are largely reflected as step changes in salinity. And for large bodies of water and river systems and estuaries, you can use these relationships to sort of identify different bodies of water throughout the world, because each body of water will have a different sort of relationship between alkalinity and salinity. These curves will be slightly different. Now, I mentioned that we can use two measurements of the carbonate system to sort of flesh out the full suite of carbonate variables that we're interested in. So in a lot of cases, sort of ocean acidification managers, researchers, sort of tribal groups may not have the funds to go out and purchase multiple instruments at once, like a PCO2 sensor and a pH sensor. So what you can do is you can rely on these alkalinity-salinity curves and use salinity as a sort of proxy for alkalinity, and then combine that with your measurement of pH and then create curves. And this is done all along the Washington coast. It's done in Southern California. It's done all over the world, just because of the limitations and funding limitations that occur with ocean acidification research. So what we have is this really nice curve that we have collected over the course of a couple of years. It's consisted of 197 check samples. We have a super nice R-squared of 0.98, so good linearity. We also have a large salinity range. So we're capturing freshwater end members. So we're capturing the freshwater that's existing in the bay, as well as the highest salinity waters. And we have a slope of about 56 and an intercept of 410. And that intercept is lower than you might find in the open ocean or in other estuarine systems. And that's largely due to the presence of freshwater, but also the fact that freshwater in Tillamook Bay tends to have lower alkalinity in general. And then we also have an RMSC of about 54. So when I say RMSC, again, it's sort of a ways to say measurement uncertainty. So we have an uncertainty in our alkalinity curve of about 54. So next I want to talk about error propagation. I'm going to slowly fill out this table and it will make sense, I promise. So we approach this as, again, sort of approaching it as a manager or somebody who's interested in ocean acidification, but may not have the funds to purchase multiple instruments and have redundancy built into the system. So our question was, can we pair our instruments, our three different instruments that we have, with a local alkalinity salinity curve, and can we propagate can we calculate the carbonate system and have like a sense of what the errors in the variables are. So for example, we looked at the SeaFET and the local alkalinity salinity curve, and we used a system in RStudio called SeaCarb. And what SeaCarb does is it takes in all of the data that we have. So we have 5 years of data, and then it inputs our alkalinity uncertainty, because again, we need 2 parameters out of the 4. So we put in alkalinity based off our salinity curve, our pH, and the SeaFET pH again was 0.036. Sorry, the uncertainty for the SeaFET pH was 0.036. And what we get are uncertainties in the saturation state of about 0.1, 54 for DIC, and then about 48 for PCO2. And the way to think about this is if you go out to the field with a SeaFET and you are trying to measure or calculate rather the aragonite saturation state, and you come up with a value of 2, you know that with the SeaFET, you have a sort of confidence interval of 0.1 for the SeaFET. So that's another way to think about this. Now we did the same calculation with the YSI. And what you notice right away is that the YSI, because of the 0.2 measurement uncertainty, which is larger than 0.036, it results in larger uncertainties in the calculation of PCO2, saturation state, and DIC. So another way to think about this is if you are, again, somebody who's interested in studying something like the flux of carbon in and out of an estuary, you're trying to figure out if it's a source or it's a sink, and you go out with YSI and an alkalinity-salinity curve, you have this pretty large uncertainty in your PCO2 calculation. And because you need PCO2 to calculate sort of the flux in and out of the atmosphere from an estuary, that value might be so large that you can't even make a decision about whether or not that estuary is a source of a sink or a source of carbon, rather. So we did the same for the SAMI PCO2. And I should note that these parentheses represent inputs of uncertainty. So that's why there are parentheses here. So for the SAMI-CO2, our uncertainty was 2 microatmospheres, which again, we think is fairly low, but that results in calcium carbonate, or sorry, aragonite saturation states of 0.07, fairly low uncertainties in pH and lowered uncertainties in DIC. And then what we did is we looked at the CO2 itself, the SAMI-CO2 and the YSI pH, and then the CO2 and the SeaFET pH. And what we get are larger uncertainties than if we just use the local alkalinity-salinity regression. So we sort of have 2 winners here. We have winners in terms of a reduction in the sort of uncertainty that's being calculated in the carbonate system variables. So the SeaFET pH and the local AlkS regression appear to work very well. And the SAMI-CO2 and the local AlkS regression also seem to work very well in terms of reducing the uncertainties in the calculated variables. So this is just a quick inter-sensor comparison. So up here we have a time series of aragonite saturation state. In the middle we have PCO2, and on the bottom we have pH. And what's important to note here is that there are discrepancies in between sensors themselves on the coast, but in general, the dynamics are largely coincident with each other. So during the summertime, when biogeochemical variability is fairly large, our sensors are able to capture that pretty well. In addition, during the wintertime, when sort of the variability is minimal, because there's not much nutrients being input to the system, the sensors are capturing that variability as well. So we feel confident that even though sort of we're talking about the YSI in terms of it having a higher uncertainty, when we're comparing the sensors between each other, just their direct measurements, we have a pretty robust comparison between pH measurements themselves and also the calculated parameters. So this is just sort of the aragonite saturation state time series blown up. And again, just a reminder that high aragonite saturation state is good for marine calcifiers, and lowered calcium or aragonite saturation state is not so good for calcifiers because they begin to dissolve back into seawater. This was a study by Nina Bednarsek with a pteropod, and it shows, again, the shell dissolution occurring in situ just in the presence of lowered aragonite saturation state waters. Now, what we've done with this graph is we've sort of highlighted at aragonite saturation state of 1.5 and below. Now, at a aragonite saturation state of 1 and below, again, it's sort of corrosive, but we know that based off recent studies that once you get to saturation states of 1.7, 1.5, 1.3, various organisms begin to exhibit stress. They begin to exhibit physiological stress, metabolic stress. And so for the Pacific oyster, which is an oyster that is fairly common to the Northwest and sort of economically relevant, that physiological stress sets in at about 1.5. And when we look at how frequently we observe aragonite saturation state below 1.5 in Tillamook Bay, it occurs about 2/3 of the time, which is pretty alarming. And if we were to calculate what the saturation state would be without ocean acidification. So if we were to take the 0.11 units away, and increase the pH and recalculate aragonite saturation state, that occurrence would be twice less frequent. So it really just emphasizes how much ocean acidification has been impacting these other parameters that are sometimes underappreciated, such as the saturation state. So I'll walk you through this. You don't have to do any math. What we wanted to ask is, how well do our sensor packages approach the question of organismal threshold exceedances? So times when the aragonite saturation state is below a certain value, but also how frequent and how long that value is. So we used a metric called Ocean Acidification Stress Index for Shellfish, or OASIS. It was developed by Iria Jimenez at Oregon State University during her PhD. Some of you might remember her. And what this is essentially, it's an integral from the time that an organism is fertilized to the time that they are settled. And it's an indicator, it's a metric or a proxy of how often that organism is in water below 1.5 saturation state. So rather than quantifying, because this is a sort of novel and experimental metric that hasn't really seen a lot of publication, we merely are sort of qualifying what this means. So what we have up here is the Trask River discharge. So the Trask River is the largest sort of source of fresh water into the bay. And then down here we have OASIS. And what you see is sort of initially that higher discharge of fresh water coincides with an OASIS value that's much higher. So freshwater has lower concentrations of calcium and carbonate. And so it represents a stressor on organisms that are calcifying in the environment. So we have these peaks during the wintertime of high OASIS values. So again, high organismal stress metrics. But we also have these peaks during the summertime when river discharge is low. And these correspond to summertime upwelling, because summertime upwelling again delivers that low pH, that low aragonite saturation state waters, and the high PCO2 waters to the bay, which again is a stressor for organisms that are calcifying. So I want to talk real briefly about meeting weather and climate goals for ocean acidification reporting. The California Current Acidification Network, or CCAN, and the Global Ocean Acidification Observing Network, they established a set of confidence intervals for determining ocean acidification in the context of long-term, what they call climate, or sort of decadal, multi-decadal timescales, and then short-term weather trends, or you can think of that as sort of seasonal to interannual. And what these values represent is if, for example, you have an instrument, you have a pH probe or some method of determining pH, and your uncertainty is 0.02, you're able to say that you can report trends in pH at the scale, at the time scales of weather, of interannual to sort of seasonal. And if your uncertainty is 0.003, you're able to report trends in pH that are based on climate. So you're able to have like sort of a statistical representation, or not representation, but a statistical significance in your findings when it comes to trends in pH. So they have these values for pH, carbonate, which is, again, saturation state, alkalinity, DIC, and then PCO2. So this led us to question, can our sensor package that we have deployed in Tillamook, is it capable of meeting any of these goals for ocean acidification detection? Like, do we have any confidence that we can make these sort of analysis with trends in saturation state specifically? So this graph, I'll walk you through this. This is sort of, you can think of this as like an error space diagram. So On the bottom, we have alkalinity error. On the side, or the y-axis, we have aragonite saturation state error. And I drew a red line where we have where we know our alkalinity error is, which is 54. And then the green and black dashed line represent the weather and climate goals for aragonite saturation state. And so the question is, do we fall in underneath any of these goals here for weather? So if we were to plot our data under weather, we would be able to meet the weather goals. And if our data fell under climate, we would be able to safely say that we can make these climate goals. Now, what these black dashed lines represent are different measurement uncertainties for pH. So for our system, this sort of upside down triangle represents the 0.036. And so we can safely say that we are meeting the weather goals for aragonite saturation state, which is pretty good. And what you can also do with this graph is you can look at it and say, what would it take for us to meet the climate goal? And you'd have to have a reduction. You'd have to move this red line over here. And then you'd have to have at least a measurement uncertainty of 0.005, because that's what these triangles are. And yeah, you'd have to have a reduction in alkalinity of about 20. So it's possible for us to get there if the instrumentation itself had a better measurement uncertainty, and if our alkalinity error was much less as well. So now I want to get back to sort of implications of measurement uncertainty. You know, what is the real world implication of why this is important? So what we have again is just the representation of what it means for high and low saturation states. And if you are a manager, or again, somebody who's just interested in ocean acidification, and you want to go out to the field and you have a YSI probe or you have a SeaFET pH, and you want to know what is the occurrence, or how frequently do we see aragonite saturation below a certain level? Well, this is called an empirical cumulative distribution curve. And all that it means, so this red curve is our data. This is aragonite saturation state on the bottom. This red curve is our data for the YSI. And if you sort of follow it up, I've drawn a dashed line at 1.5. So the threshold that we think is important for sort of organismal stress. If you come up here, right here says 0.5. That means that 50% of all of our observations are below 1.5. So 50% of all of our calculations of aragonite saturation state for the YSI are below 1.5, and 50% are above 1.5. However, this doesn't take into account the fact that we have an uncertainty of 0.2 units in pH. And when we apply that uncertainty, our confidence interval grows to this very large number between 9 and 81%. So we basically have an occurrence of, you can only confidently say that between 9 and 81% of values at 1.5 fall below 50%, which is sort of a large number. When we apply this same calculation to the SeaFET, because the SeaFET has a much smaller measurement uncertainty, that number shrinks between 61 and 77%. So you're able to more accurately go out into the waters and say, okay, we have this sort of confidence interval with which we can use to define how frequently or how often we see the aragonite saturation state below a certain value or above a certain value. This can be moved around. So just some conclusions and lessons learned. High quality data greatly increases the confidence in characterizing threshold exceedances, which is critical for evaluating acidification stress in organisms. We found that the SeaFET pH plus our local alkalinity-salinity curve, or the SAMI-CO2 with the same curve, is the best combination to sort of reduce propagated uncertainty in the carbonate system. Future work should include a comprehensive assessment of data quality requirements to assess acidification in estuaries. And then some future work. Our data is still ongoing. We're still collecting data. And data has been submitted to the state for water quality evaluation. And if you're interested in seeing that data from Tillamook, QA, QC'd, and published, you can look up Rosenau et al. 2021, which is up there. Work continues with the Tillamook Estuaries Partnership to continue understanding ocean acidification in the Bay. And what we learn will continue to be useful. The data synthesis we feel is fairly novel, and it spans 5 years of continuous data with multiple sensors. So we have an amount of redundancy in the measurements. So I just want to say thank you to all of our collaborators from all of these divisions and parts of the country. So thank you.
All right. We're going to go to questions, and we're going to start with, is there any questions online, Roseanne? Okay, so for folks online, if you've got any questions, go ahead and put them into the chat box and we'll get to them. How about questions in the room?
Thanks, Will. Just really great work. I have a question about, I think it's slide 29 maybe, or a couple back, that shows the difference in uncertainty between the two instruments with the your half sort of accumulation curve. A couple of slides back.
This one?
No.
We'll find it.
No, it's near the end. Yeah, so it's that one and that one. And
okay.
So what it appears to me that one of the key differences there is not just the uncertainty interval, but the where your red line crosses your dashed black line there between the two is quite different, right? Is that
between the sensors themselves?
Yeah, I'm just trying to, yeah. So one is at, close to that 50%, right? Over there, the cumulative distribution.
Yeah.
And the other one is much closer to, I don't know, 73%, something like that.
That's right.
And so that seems to be a key part of that difference, and also in the spread there. And I'm just trying to make sure that I understand that correctly. Is that accurate, or am I missing something there?
No, that's accurate. And that has to do with the fact that, the sensors are not the same, and the measurement uncertainty is just so large that, even when we get a measurement and we just plot the red line itself, if you take multiple YSIs, because there just is that uncertainty, and you were just to plot a bunch of red lines on top of each other, they would all look slightly different, whereas the SeaFET has a much less uncertainty to it.
Right.
Yeah.
So that gets back to why the SeaFET appears to be a better instrument for getting better accuracy and less uncertainty.
That's what we believe, yes.
Okay. Thank you.
All right, looks like we got a question online. Go ahead, Roseanne.
Have you done any outreach on this work to guide future monitoring programs?
So, right, we have just submitted a manuscript for review. Our outreach is ongoing and sort of in the early process, especially with this work in particular. But we hope to, bring in as many collaborators as possible, because we think that some of this work will be important for especially communities that are funded by or limited by funding, right? Because it's important to have access to instrumentation that you can trust in order to sort of fill out the carbonate system and sort of make these time series analysis of different carbonate variables. So the short answer is no, we haven't done much outreach yet, but we are planning to.
And Will, to add to that, can you talk a little bit about the issues that we've been having with the SeaFET and others getting instrumentation?
Which are you specifically referring to?
That we don't have a chip, and so we don't have any on hand to be able to purchase and calibrate?
Yeah, so that is something I didn't mention, is that the SeaFETs themselves are limited in availability currently. And that's largely due to the fact that there was a limitation in chips in like computer chips, sort of nationally for the last several years. And so they have temporarily, at least I believe temporarily, stopped funding production of new SeaFETs and also calibration of SeaFETs, because these SeaFETs are built so all of the calibration coefficients of the instruments themselves are stored within the instrument, and you have to send it back to the manufacturer for them to recalibrate the instrument before you can get it back into the field. And currently, they are not accepting any SeaFETs currently. So that is definitely a main sort of hindrance of this research, is that, hey, we found this really cool thing that we think works really well, but now suddenly the manufacturers are sort of halting the temporary like work on them.
Yeah, it's definitely, from what we've heard, temporary, but it's something to just be aware of as we all get really excited about SeaFETs. All right, questions in the room?
Do you see potential application of this on other estuaries, say in Washington and Oregon, that would be useful to have long-term monitoring data that maybe at slightly different conditions than Tillamook, but have high amounts of shellfish fisheries of commercial interest, like Yaquina Bay or maybe even further south?
Yeah, I mean, that would be fantastic. I think there's not enough OA monitoring in general. So the more that we can fund and the more that we can sort of get the word out and say, hey, we really need to understand the spatial variability in these metrics, that would be fantastic. But, funding is a huge crux in this field. And unfortunately, that's just how it goes. But we would love to see more funding and more research in these sort of long-term time series of ocean acidification.
Brett, did you want to answer something? You were shaking your head. Did you have a... Hang on a second. Oh, sorry.
Part of that funding might be not only the instrument, but for your crew or a crew, whatever crew, to go out every month and maintain the instrument, obviously.
Exactly. I mean, that is a key thing too, is that we have this mooring set up in Tillamook, and T. Chris, who's in the audience, and I go out once a month or so, and it's a full day. It's, manpower, it's a lot of work, it's a lot of equipment, it's reagents, it's all sorts of stuff that you need to bring with you. So it's not as simple as just taking an instrument and plopping it in the water and then walking away. It requires a lot of maintenance and upkeep, and also technical know-how to keep those instruments up and running, So that's a big limitation as well.
I'll just throw into the audience and into the world that having a network of folks that have the expertise like Will, and to be able to move from sample location to sample location would be a really interesting thought. So just throwing it out there. All right, it looks like we have another question online.
Yeah, I have a comment and a question. The comment is, great job, Will. We'll miss you in Newport.
Oh, thanks.
And the question, what methods did you use for your alkalinity-salinity local curve? How would a change in error within alkalinity or salinity change your 54.5 RMSE? So
if I got that question correctly, they're asking, how would the salinity curve change? Can you repeat some of that again?
How would a change in error within alkalinity or salinity change your 54.5 RMSE?
Well, I think, first of all, the methodology, if that was the first part of the question. Okay, so the methodology.
What methods did you use for the local curve?
Okay, so we used our check sample data that we have taken. So we have about 197 check samples that we have taken. And we used this instrument called the Percolator, which is a sort of proprietary instrument. And we run our samples through this instrument, which is can measure PCO2 and dissolved inorganic carbon. And if we have temperature and salinity at the concurrent time that we are sort of taking these samples, we can calculate out alkalinity. I think if we increased the sort of ability to reduce uncertainties in the alkalinity curve itself, it would come through the methodology that we are arriving at alkalinity. So we would need to refine sort of the methodology itself to say, okay, for example, there's some outliers on this curve. How do we get those outliers to fall more cleanly with this linear relationship that we've built here? And it probably has to do with, there could be something as simple as like a transcription error. Somebody wrote the wrong temperature, and then so we get, inaccurate data. It could have to do with user handling. It could have to do with other sort of methodological problems like that. So that would be a way to sort of refine this curve and get the RMSE to be much nicer.
Is this curve available for other estuaries besides Tillamook?
Is this curve available? So this curve actually, it's really similar. This slope and intercept is really similar to work I did in graduate school. In graduate school, I worked at Netarts Bay at the Whiskey Creek Shellfish Hatchery. And there they actually are running continuous measurements of PCO2 and dissolved inorganic carbon. It's sort of a novel place where they really have high resolution data. And the curve in Netarts Bay, which is just like, I think 20 miles south of Tillamook, has almost an identical curve and intercept as this one does. I have actually looked at plotting other curves on here that have been published regionally, because there are regions like the Pacific Northwest, the Washington coast, Northern California. These regions have specifically, like, they have published alkalinity-salinity curves that have been, published and adopted. But the utility of having one specific to Tillamook is the fact that, we're trying to calculate out other carbonate variables as well. And if our alkalinity curve is off because we're using some other regional metric or some other regional product that may not be reflective of the salinity dependence of alkalinity, then we could get wildly large errors in things like PCO2 or saturation state.
Is there other questions in the room? Hang on.
Oh.
Hang on.
So this is a little bit of a two-part question as well, because I want to make sure I understand the first part before I ask the second part.
Okay.
So when you talk about your uncertainty values, does that equate to like measurement error of the device, or does the uncertainty like associated to that measurement error through the relationship of the multiple measurements?
Oh, so I think you're talking about
Any of the instruments that are measuring pH or something like that.
so let me make sure, because I also talked about error propagation.
Yeah.
Is this what you're referring to?
So there's the error propagation, but then you also mentioned for looking at climate versus weather, you had an uncertainty value, I think, or an error value of 0.02 versus 0.003. And so does that correspond directly to like how much error there can be in a given measurement, or is that translated in some other way?
So I think your question is, or the answer to that question is, the 0.2 is a manufacturer-based value. We didn't have a method developed to look at the YSI and come up with our own value of uncertainty for the YSI. Similarly, so this 0.036 for the SeaFET pH is pretty much in line actually with some published values that use much higher quality, or I wouldn't say higher quality, but they use different methodologies to sort of attune that curve, that uncertainty curve. I think that answers your question.
I think maybe I just don't quite understand it well enough, but
Okay,
then I guess the other part is, given some of the thresholds that you talked about, are there instruments that do operate at those levels of uncertainty, those much lower levels of uncertainty, where those sort of legislative thresholds are set?
Part of the reason that this work is unique is because we're characterizing uncertainty within an estuary. So estuaries are such dynamic environments that if you go out to the middle of the open ocean and you were to, say, deploy a SeaFET and do the same calculation in the open ocean where there's much less variability, you might get an error of like 0.005 or something. So it just has to do with the fact that there's so much variability in the system itself that we can only constrain our understanding of the uncertainty to a certain degree.
All right. Questions online, Roseanne? Greg, do you still want your clarifying question?
You mentioned the work in Netart's Bay, and we were looking at the curve for Tillamook Bay, but if my understanding is correct, Netart's doesn't have that same sort of freshwater input. There's essentially almost none. And so the graph that you showed for Tillamook Bay, and one of the things that you said about it was that it went down to that nearly zero sort of salinity sort of thing. And so, and also you mentioned that the stuff in Netart's was almost continuous. So your N is going to be a lot higher than 197, if I understand that correctly.
Yeah, it was in
and
the
your
thousands.
salinity is not going to be anywhere near down to close to zero. So the two, while you said that they were very similar, I would imagine that they're very similar up at the higher salinity values. Is my understanding correct there?
That's correct.
Okay.
But
Thank you.
the sheer magnitude of samples that were taken, because it's in continuous mode, sort of functioning at 1 hertz almost, even though low salinity events in Netart's are not as common, right, because it's a mostly ocean dominated estuary, you still capture some of that freshwater end member regardless, just because also Netart's is very shallow, and it tends to drain pretty quickly. So even in the winter months, you have all this fresh water entering the bay, but it's so shallow that it pushes out the salt water. You don't really have. Does that make sense? So you are capturing some of the freshwater end members in Netart's, but it's largely, you're right, it's largely controlled by the higher salinity values, the alkalinity salinity in Netart's.
Yeah.
I think that's something that I would like to sit down with somebody who does hydrological modeling and figure out if there even is a saltwater wedge that is very apparent that you might see in deeper estuaries, but Netart's is so shallow that at low tide you can just walk across the whole bay.
Okay, thank you.
All right, we're at time, but I also just want to make a little plug that the work that Will has been doing in Tillamook, we are trying to repeat here off the end of our bay, right here off the end of our pump house. So we will have a percolator hopefully in play by the end of summer, SeapHOx, we'll SeaFET and the XO. So we'll be able to look at some of the same information here for our bay. So we're excited about that. Anything else, Will, as we wrap up?
No, that's all. Thank you.
All right.
Appreciate the questions.
Thanks, everybody.